Now let's do the share screen. Yeah, can you see my screen?
Yes.
Can you see me? Why does that doesn't work? What happened? When all my deadlines are over, I'll have some good time, then I'll sit down and I'll give all my lecture notes to you. I know it's recorded, so prepare for that. Because the problem is that I'm preparing them, but there are a lot of typos in them and that, so I don't want to put them. Okay, so today we have both tutorial and lecture. I'm actually going to start with the tutorial again. It's easier for me because I never know how long it's gonna last. And I prefer that we finish with the tutorial before I give you the problem set. Now, one of you asked me about if I can extend the problem set. But generally, the answer is yes. If you need any extension, then I normally give it to you, but you have to ask it in advance. Don't tell me, oh, if you don't tell me that in advance, this is not accepted. But then one of you asked me if I can extend the deadline for submissions until Friday noon rather than Thursday midnight. I don't mind, really. It's really up to you. Don't delay with that. There's no point. Okay, so let's start with the tutorial. So I want to do a tutorial. Tutorial. So it's number 4. It's about decay and cross-section. And the reason I prefer to start with it is I said I'm going to give you a homework later on about that. So it's, I don't think it should be very long. It's mainly things we already discussed. So let's start with decays. So as we said, right, when we speak about free particles, right, the wave function of a free particle is psi of x mu, right, proportional to e to the minus I p mu x mu, right? And if you're in the center of mass, right, then the special components are 0. So we have psi of t, right, is proportional to e minus I m0 t. I assume you're familiar with that. Am I right? If you're not, I know that some people tend to participate a lot and some others tend to be very quiet. And I also know that there are people at certain levels here. There are some people who are master students and some people are undergraduates. So I actually do want to encourage the undergraduates to participate more. The course is supposed to be accessible to undergraduates, not just to master's students. Or higher, of course. Okay, so psi of t goes as e to the minus I m0 t. Now, if the particle is not stable, right, so non-stable particle, right, that means that we are really interested, right, in the probability of finding the particle at time t. So this will be psi of t squared, right? Is associated with the probability of finding the particle at some time t. Right? And of course, it vanishes when t goes to infinity. So the way to do it right, is we're adding a term to the wave function. We do it by adding a term to the wave function which now becomes psi of t proportional to e minus im 0t, but then e minus gamma t. Now this addition really affects the mass of a decaying particle, right? Because how it works, we just apply a Fourier transform and we look at the wave function in the energy domain. Okay, so we make a Fourier transform. And then look at the wave function in the energy domain. So psi of m, right, is integral from minus infinity to infinity of psi of t times the Fourier transform eimt dt. And the answer to that is just I over m minus m0 minus I gamma over 2. So what we really get is the mass distribution of the decaying particle. That is, that reflects the probability of measuring the particle with a mass m. Right, so you should write it down because that's important. This gives the mass distribution for the particle. Right? Namely, reflecting the probability of measuring it with mass m. Right? So the probability density which up to a normalization constant, right, is just taking the norm of that. Right, up to a constant. Psi of m squared is 1 over m minus m0 squared plus gamma squared over 4. And this is what is known as the Bright-Wigner distribution. So if I want to plot it, right, it will look something like that. It's the probability to 1 of psi of m. Well, this is the center, right? It's this m0 c squared, and then it's a plus minus gamma. Right? It will look something like that. Where exactly half the width is exactly gamma. or you can use your favorite plotting software to plot it. So the several properties, right, that it picks at m of m0, right? Width is gamma, right? The particle lifetime right, tau is 1 over gamma. Right. Which means that when we have a stable particle, right, such as the electrons and the protons, we simply don't have this width, right? For a stable particle, right, gamma is 0. It's a narrow, right? So a few more comments is that the gamma, that's the important thing. I mean, it sounds a little bit non-intuitive, but gamma is the characteristic of the particle, right? It's not the measurement. It's the actual particle's mass. Right. So for stable particles, there is no width. Right. That I already showed in class, right? That experimentally, this is quite crucial because this is a way of discovering new particles. Right? You discover new particles first by the resonance. Right? That's how people saw the Higgs. Right? You saw the resonance. You don't see the particle itself. Its lifetime is way too short to be detected. Right? So experimentally, right, new particles are discovered or can be discovered, right, by measuring the energy of the decay products. Remember, if the particles were long enough to live, then we could see them directly. But the fact that we don't see them, that means that if they are there, they're simply too short-lived, right? So the way to detect them is just looking at the outcome, right? So the energy of the decay products and observe a resonance. Well, I show you the resonance for the W boson. Now, the decay, a particle can normally decay into several different ways. And the terminology for that is channels. So we have a decay channel, right? Now each can have a different probability. So let me write down particle can decay in several different ways. These are called channels. 1 N or 2 N's? I think it's 2 N's. Right? So each has a different probability. And the total width, when it takes all the, means that we have to take all the channels into account. Right? So the total width And gamma is simply sum over I of gamma I. All right, questions about that? Okay, if not, then I have a question for you. So let's do an exercise. Question. So consider a charged particle, a charged pion decay. Right, for example, the pion decays into a muon and antineutrino, neutrino muon. So, one, what are the energy and momenta of the muon and the neutrino in the pion's rest frame? And part B would be assuming that the decay occurs in a vacuum, let's say in space, what is the typical distance the muon will travel before it decays? Well, let's say not in space, let's say that it happens in CERN on a daily basis. So what is the typical distance the muon will travel before it decays itself, right? The muon itself is not stable. Now, just that you know that in the muon's rest frame, the muon's lifetime is 2.2 microsecond. And I want the answer in regular units. This can be meters or centimeters or kilometers, but not electron volts.
The distance in the pi's frame of reference, right?
Yeah. Yeah. It's a very relevant question, right? I mean, you're producing pions in the lab. It's actually quite easy to produce them. Many cosmic rays use them. They're the leading mesons that are being produced. And now they decay. They're not stable. Actually, that's one of the major sources of high energy neutrinos. I don't know if you're aware of that. In the South Pole, there is a large neutrino detector. It's in the South Pole, the geographic South Pole, deep under the ice, 3 kilometers deep under the ice. And it's aimed at looking at very high energy neutrinos. And actually the decay is one of the ways to get these neutrinos. That's the outcome of high energy cosmic rays that come. So, who's volunteering to answer the first part? What are the energy and momentum of the muon and the neutrino muon that are produced in the pion decay?
Is this anything more than solving two equations in two variables, where the equations are the mass and linear momentum conservation in an arbitrary direction?
Well, in principle, yes. In practice, we need to do it using the four momentum formalism.
of course. So for we need the rest mass of the pion from the book.
M pion.
From the
M pion. So what's the
M
okay?
pion.
So one by one. What is the pion? How do you write? What is the form of 4 vector of the pion?
MPPX.
What is that?
MP, comma PX, comma 0, comma 0.
No,
Nope.
actually just 0, 0, 0.
Correct. In the rest frame. What is the form momentum of the muon? Somebody else? Let's call it P1. Yes. Come on, guys. Okay, it's not a big class. Definitely here. There you won't have anybody to consult with. Come on, how do you write the form momentum? Okay, I can wait. You know, this is the point that I tell, look, a few minutes ago, I asked you if you have any questions, and you said no. And for me, that means that you should not have any problem answering this question. How do you write down the form momentum of the muon? I mean, what do we have here, right? We have a pion in the rest frame that decays into a muon and a neutrino, right? We're in the rest frame, right? So I can choose a direction. So let's say that I can say that the muon is moving in the z direction, right? So the form momentum of the muon how do I write it? Do you want me to give you more exercises about 4 momentum and 4 vectors in general? It's a serious question. It's not any punishment. This is something which you shouldn't cause any trouble to any of you. If you need to practice that, I'll be happy to give you more things to practice. I'm really serious about that, guys.
I could use some.
Okay. Let's say E1, 0, 0, P1. What's the relation between E1 and P1? It's an open question for everybody. What's the relation between E1 and P1?
E1 squared equals P1 squared plus mu on mass squared.
That's true. Very good. E1 squared is P1 squared plus M mu1 squared. Is that clear to everybody? That follows from the Einstein's relation. We learned that in special relativity in the beginning. right? It really should be c squared here. I mean, there are a lot of factors of c that are gone, right? There's c squared and c to the 4. But since we work in natural units and c is equal to 1, then I don't care about the c's. What will be the form momentum of the neutrino?
The same thing on with minus.
Very good. So it has the different energy, right? Very good. Because it's in the center of mass. Okay. Now, what do I do with the 4 vectors? So these are the 4 vectors of momentum. What do I do with them? What are the conservation laws that we have? What will be the first conservation law?
Momentum.
Yeah, but I would start with something which is even simpler.
Energy conservation.
Energy, yeah, right. So what does conservation of energy says?
U pi would have to be the sum of E1 and E2.
Correct, very good. So conservation of energy. Right, pion is E1 plus E2, which means that E1 I can write as m pion minus E2. Now the simplest, of course, is to square that. And we get E1 squared, right, is just m pion squared plus E2 squared minus 2 m pion E2. Now is where I plug in the relation between the energy and the masses, right? So E1, I can write as P1 squared plus m mu1 squared, right? Which is m pion squared plus m neutrino squared plus P1 squared, right? Minus 2 m pion E2. So E2 is just m pion squared plus m neutrino squared minus m muon squared divided by 2 m pion. Okay, the rest is just to look at the table of the masses, the PDG. So I can just give you, I mean, you know, but to get here, you don't need to know anything of the masses. This is the right answer, right? So the rest is just to plug the numbers. So if you put the numbers, m pion is about 140. That's what I remember. The exact value is 139.6 MeV. M of the muon is 105.6 MeV. What is the mass of the neutrino?
Almost 0.
0, that's right. So we can simply put it as 0. So if you put it, then you end up with E2 of, I got 29.8 MeV. And then of course E1 is just m pion minus E2. So that's 109.8. Not particularly difficult, I think. Unless you get confused, then it can be really difficult.
E2 was the energy of the muon?
Yeah.
How can it be less than the rest mass?
E2. Sorry, E2 is of the neutrino, not the muon.
Oh, okay.
The neutrino muon.
Okay.
And the rest mass we just said is 0. Okay. What about part B now? The problem, part B says, what is the typical distance the muon will travel before it decays itself? I actually give you the lifetime of the muon in the rest frame, so it's 2.2 microseconds.
They use the momentum to get the velocity.
Right, right. So what is the time? How it is related to the tau? What is the time? As measured by somebody.
Equal to
Sorry?
gamma times tau.
Gamma times tau, very good. Gamma times tau. And what is the distance that it travels? What's the formula for the distance that it travels?
Velocity times time.
Right, that's true. What is the velocity? How do you write it? Oh, that's true. It's velocity times time. That's always true. And how do you write the velocity?
Divide the momentum by the mass.
Newly? Well, actually, yes. So I write it as beta CT, right? So overall, this is beta C gamma tau. Right, so I can write it down as the momentum divided by the mass. Very good. So this will just be the momentum, P1 C divided by M Muon C squared times C tau. Right. These two C's cancel out, the nominator and denominator. Right. This is just a 29.8 MeV. We had divided by 105.6 MeV times C tau. So this is the actual unit that we need. So this is 3 times 10 to the 8 meters per second, and this is 2 times 10 minus 6 seconds. So it gives us 170 meters. Right? P1 is M, U1 gamma beta C. Is that clear?
I think you have an extra C.
Where? What did I miss?
C squared divided to C squared. So why is there another C when you plugged in everything?
Yeah, but the mass, when you take the mass in units of electron volt and the momentum in units of electron volt, the C is already built in.
Ah, you can, okay, because you convert it.
Yeah. It's already built in, right? It's MC squared really. It's a little bit of practice. It's not much more than that. And remembering that E is equal to MC squared. That's not very hard.
Seth?
Yeah.
How does the finite lifetime of the pion come into this calculation, or the finite lifetime of the muon, can we just use the muon mass without any width? Isn't there any randomized or something like that?
There is a width, of course, to the muon mass because it decays.
Perhaps I'll rephrase. You said that the width is a property of the particle and not of the measurement.
Correct, yes.
But does it mean that the particle behaves like it has intrinsically random mass, or does it behave that it has a well-defined mass, but any measurement, no matter, doesn't matter how precise and how smart and whatever, will observe some uncertainty?
No, you observe there is a probability of detecting the mass. This is the bright Wigner.
So is this a probability of detecting the mass that is uncertain intrinsically, or is it the mass itself random?
Well,
because it sounds very, very foggy, but actually we use here an exact value of the mass. We use here muon with exact mass, whatever it was, 105.6.
Yeah, this is what I call the M0 in the bright Wigner formula. Right? This is the M0. And now, when you make an actual measurement of the muon mass, right, then you'll end up with the bright Wigner distribution.
Yes.
Right. Now, the 105.6 is exactly what is denoted here as M0.
Yes. So this muon that doesn't live forever, if we try to detect it, we'll have some width of the mass. But when we calculate, not when we measure, but when we calculate the behavior, E muon squared minus P muon squared is exactly M0. Or is it something within a range of gamma?
No, it's exactly M0.
Okay, so this width, this bright Wigner width, gamma, is a property of every detector. So it's a property, it says how good can we detect the mass of the particle, but it doesn't mean that the particle itself has an uncertainty in its mass, just that we can detect the exact mass, right?
No.
I don't think so. No, it's a superposition, right? Yeah, it's a superposition. So it's a part of this property.
But essentially, no, but if it was the particle property, then we would have had a probability that a muon here will have energy and momentum that correlate to mass of 106 or 105.
Right. No, you're right. You're right that it's a subtle point, but no, the uncertainty in the mass is intrinsic to the mass.
Is it to the mass, but only to measurements of the mass, not to.
No, it's the actual mass. It's the actual mass. When you actually do the experiment, right, then there will be an uncertainty here, right? Okay, you're right that this. I'm taking a very simplified example, as I should in this course. But you're absolutely right that the muon mass, right? This is M0 muon, right? To be on the safe way. Oh, what did I do? To be precise, this is M0 muon. Right? When I quote the value of the mass from the PDG, right? I really quoted the M0.
Yes.
Okay. But the actual mass of the muon that will be produced following the decay of the pion will be drawn from the bright Wigner probability.
So if I have a detector of diameter 1 meter, so all the muons, no muon actually decays into something else because it takes 100 meters. So I take a detector of diameter 1 meter, and I have a very good detector, so I find each single muon and write exactly the energy and momentum that I observe. Would I get exactly 29.8 every time?
No.
No. So you'll have
a distribution.
Okay, and this distribution results from the distribution of the mass itself.
Yes.
So one muon will behave like it has a mass of 106 and will have slightly lower energy, and one will have effective energy of 105 and it will have slightly higher energy.
Correct. Yes. Yes.
Okay. And this energy is consistent. So that will be true if we measure not the muon, but the electron resulted from there, etc. Right?
Well, sometimes the way you detect the muon is by looking at the decay product of the muon itself, right?
So
muon,
when a
the
muon
is long enough that you can actually see it tracked in the detector.
Yes, that's why I talked specifically about the muon. So so when a muon is generated, when a muon is born, it gets a mass, and this mass is withdrawn from the Bright-Wigner distribution.
Correct.
And it carries this mass consistently. So it has one mass, and this mass is drawn from the Bright-Wigner distribution.
Yes.
And this mass follows forward towards when there are for the say next processes, etc.
Yes. Yes.
Okay, thanks. That
Very good.
makes a lot of sense.
Okay, very good. So yeah, it's a it's an important point to emphasize. I wrote down when you look at the PDG, I think it's written in there actually. You go and look at the muon mass, they will tell you this will be corresponding to the M0, to the center of the mass. For muon, I don't care too much, right? And also it's very well measured because the lifetime is so long. But you have other particles whose lifetime is much shorter by orders of magnitude, which means that the uncertainty is much larger.
I think this question also kind of relates to if you're ready to accept the Copenhagen interpretation of quantum mechanics. It's a very deep question, right?
Yes, sure. You have superposition of these processes. You have a muon is generated with as a superposition of these, and you have a correlation between the mass and the energy or momentum you create. Sure, but what I try to make sure is that when we met a single muon in a single word line has a well-defined mass. So when a muon is generated,
I don't think that's true. I mean, the way I understand quantum mechanics, I don't think that's true. I think a muon is in a superposition of different masses, the same way it's in a superposition of different momenta.
Okay.
I think we should continue this discussion
sure.
Here. I think you made a very good point, and I think I tried to answer to the best of my understanding, and I think I gave you the right answer as far as I know. So, all right. If you want to go to philosophy and somewhat deeper into the philosophy of quantum mechanics, then maybe we can do it later on. Okay, let's proceed on. So this was this example. Now I want to say a few words and say, I know it takes more than 45 minutes, what I'm prepared. But it wouldn't take much long because I think the concept of a cross-section, I want to make another short review about that, and then that will end up the tutorial, and we could resume back to the lecture. Any further questions about the decay before I proceed? Okay, so let's make a small visualization of the idea of a cross-section. So remember, the cross-section is something which is relevant for a given process and is defined as the ratio of the number of particles that are being scattered from a target per unit time by the flux of particles hitting the target. So it's number of particles scattered from a target per unit time, which is divided by the flux of particles hitting the target. Now, the flux of particle hitting the target, right, is the number of incident particles per unit area per unit time. Number of incident particles per unit area per unit time. Now this is the flux. Right? We said that the cross section sigma has units of area. So typically centimeters squared, but the true common units are barn, actually nanobarn and less depending on the processes. So this is, normally people think of it in terms of billiard balls, right? So it's the effective cross-sectional area of a target as seen by the incident particle. But of course, this is nothing to do with the physical size of the target, right? Now, sigma is a characteristic of the process, right? So it can have the same particle, but undergoing different processes, it will have different cross sections, right? So it's not the target, it's the process. Sigma is a characteristic of the process. This is a Lorentz variant. Question? And for different processes, the total cross-section is additive. Right? So sigma, let's say proton plus proton goes into something, is sum over all possibilities of the sigmas proton plus proton goes into xi. Now, it is often useful to discuss the differential cross-section, right? D sigma d omega. This is the number of particles. This differential cross-section. Is the number of particles scattered from a target per unit time into a solid angle d omega. Scattered from the target per unit time into solid angle d omega divided by the flux of particles hitting the target, of course. Now, of course, total cross-section is integral over all angles of the sigma d omega. So, concrete example, right? So let's say that we have, some particle of type A type particle, right? That is moving with velocity VA, right? Traversing a region of area A that contains some density. So we have a region, area A, that contains a density NB, particles of type B. Right, so let's say A. Is A. A top particle, right? And move at VA, of course. And the B particles move at VB. And there are NB particles, type B particles per unit volume. And they all move at velocity VB, right, in the opposite direction. So in time delta t, right, the particle of type A, right, traverses a region where there are delta n, which is just NB times VA plus VB times A delta t particles of type B in time delta t, right? We have delta n particles of type B. So the interaction probability by the way, the cartoon is clear to everybody? I don't foresee any major difficulty, but I just want to make sure it's on the safe side. Is it clear what is being drawn here? We have a tube of area A. There are particles and the A type, the red particle is moving inward. There are B particles of some density NB that moves in the opposite direction, right? And the interaction of probability is the effective cross-sectional area of this delta n particles, which are divided by the area A, right? So interaction probability is delta P is just delta n times sigma divided by A. Which is just NB times A VA plus VB times delta T times sigma divided by A. So NA cancels out. So this is just NB times sigma times VA plus VB delta T. Now this is for a single particle. If we have a beam of particles, right, it's for a beam of type A particles, right, there's a number density Na, right, which are all confined to this volume V. Right, so now I'm introducing many A-type particles. Right, and the rate of interaction What's the rate of interaction? So it's a rate, right? So it's the probability of interaction per unit time times the total number of A particles in an area. So that's times NA, sorry, just the total number of particles, right? So NA times V. So this is just NB V sigma, where V is just VA plus VB. This is the relative velocity. Times NA times the volume. Which we can write as NA times the relative velocity times NB times the volume times sigma, which is NA times the velocity, relative velocity. This is just the flux, right? So this is just phi A. NB, this is the density times the volume. This is just the total number of target particles, NB. And sigma is the cross section. So NB is just NB times volume, right? Phi A is just NA times the relative velocity, is the incident flux. Of incoming particles. It's the A type. Or we can write down that sigma is just the rate of interaction, R, divided by the incident flux times the number of target particles. Is that clear? No questions, no comments? It's quite straightforward, I think. You know, maximum takes a few minutes to see, but it's easy to visualize what's happening here. Okay, and one last thing I want to say about that is the luminosity, right? So the rate of interactions is proportional to the cross-section area for the interaction, right? So the rates, right? dnx over dt is just the flux phi A times total number of target particles times sigma x. So phi A times NB is the luminosity. So this is the luminosity. This is the definition of the luminosity. Right, this is the rate of interactions, right? So we have dnx over dt. It's just the luminosity. I write it with a curly L times the cross section. Now, of course, the advantage is that this L is something which we control in the lab, or at least we can measure. You know, have some way of determining, right? Experimentally. This is because controlled experimentally. Right, so we choose the target. We have some control of the incoming particles flux, right? The velocity, the density. This is something which we actually have a control over. And dnx over dt is something which you can actually see. This is what we measure in the experiment. Right? So that's how we can deduce. So opposed to that, right, sigma x is something which we measure. This is control. This is measurable. And this is something that is controlled by the physics, really, right? This is the nature. Now, this is the rate of interactions per unit time. If you want to see the total number of interactions that occur in the experiment, right, we must integrate over the time. So the total number of interactions in a given experiment is given by integrating over time. So that gives us the integrated luminosity. L, let's now write this regular L, just integral of the curly L times dt. And then one last comment is that we said that the relevant units for cross-section is the Born. The Born. 10 minus 24 centimeters squared. Centimeters squared, yeah. But in reality, for most processes we are interested in, it will go with the region of nanoborn, even down to femtoborn. And I said when we speak today of detecting dark matter particles, they go 10 to the minus 20 barn or so. So that's, I'm not even sure how to write it down. For the luminosity, the units of the luminosity, this would be centimeter minus 2, second minus 1. And for integrated luminosity, let's integrate it over time, so it's just centimeters minus 2. Which more often will simply be femtoborn to the minus 1. And that depends on the experiment. Questions? Questions?
I have a more conceptual question.
Try me.
When you talk about elastic processes,
Yeah.
how do you set a cutoff of when the process does not happen? Meaning, if you have, say, an electron scattering,
Yeah.
then no matter what the distance, what the impact parameter will be, there will be some small effect on the scattering electron.
Yeah.
So would you say the cross-section in that case is infinite?
Yeah, we discussed that. I showed it, I think, last week.
And would
Divergence.
that be the case? And that would be the case for any elastic process, actually, right?
In fact, yeah, I think you can get into some, things get somewhat vague when you run out of causality. Namely, the electrons are so far that, the distance between them, they cannot interact. The time it takes for interaction, right, is cannot be more than the speed of light in principle. They cannot exchange information.
Yes.
But in quantum field theory, there is actually a way of overcoming this as well. It's kind of a nasty, though. Nasty
All right.
mathematical trick. But yeah.
Okay. Thanks.
Okay. So, I somehow have to adjust the times that I'm doing that. I mean, I told you I have access to the course that was given in Tel Aviv, and I know that's what they do there. But somehow for me, it takes more than an hour, though it's supposed to be 45 minutes. I prefer to take it slower. I told you, I don't care if we skip one subject, but the rest we understand properly. It's much better than to rush up and then you don't really understand what I'm talking about. But the underlying assumption is that if I go slow, then you actually understand. So if you don't, again, it's your responsibility to let me know. I cannot read your minds. I can see what you do at homework. I can see the questions that you ask, but I cannot do, and I will see what you do in the exams. But if there's something you don't understand, you want to make sure that it's cleared way before the exam. And we still have time, right? We're just in the middle of the semester. Okay, so I said that we're going to the fun parts. So in the remaining, I don't know, 20, 30 minutes, whatever we have left, we are going to do quantum mechanical description of the photon is the main subject that we're doing right now. So we started it already on Tuesday. So it's a Maxwell's equations. Photon. What? Maxwell's equation, the photon. What?
Perhaps the case doesn't sit well on the iPad.
So I feel it. No, I feel that this just wants to annoy me. The photon, and we will get to Klein-Gordon and Procca equations later on, but I don't think it will be this week. I'm actually sure it's going to be next week. The photons and Klein-Gordon equation. So we said, quick recap, right? We said that in classical electrodynamics, the interaction arises from the fields, right? Every charged particle has its field, and another charged particle respond to the fields that it feels of the other charged particles. And that changes its trajectory. And we call this scattering, and we call this force, essentially. In quantum physics, everything is being quantized, right? Everything becomes a particle. And the particle that is associated with the electromagnetic field is the photon, which means that photons need to be involved in any interactions. That's why in quantum electrodynamics, every interaction is being described by an exchange of a photon. That's the virtual photon. Now in classical systems, right, what happens is that there are very many photons that are being exchanged between the particles, and all of them have low energies. So, it's all the discrete photons together end up with a field, right? Very similar to what happens in Young's double-slit experiment, right? We have a lot of photons and we end up with a wave-like behavior or field behavior. Now in quantum mechanics, right, then it's the opposite. We have an exchange of very few photons, and so the discrete nature of this event becomes apparent. What's happening? Do I feel I'm losing students around? I don't know what happens.
Something happened at the university.
Yeah,
Something happened at the university.
everyone's back now.
Yeah, I just realized I was losing students for some reason.
Yes, there was a fluctuation on the Wi-Fi in the university.
I told you it's raining, right? Every time it's raining, then something must happen. Anyway, so I said that when there are many exchange of a lot of lower energy photons, we're seeing a classical description, and when there is exchange of a few number of photons, but they are energetic, then we're seeing a quantum mechanical description. That's what happens when you have a collision of high energy, Compton type collision, when we have the photoelectric effect, etc. Now, okay, we spoke about units, we spoke about Maxwell's equation, and I told you that I can put the electric and magnetic fields in a covariant form, which forms a tensor. I did not fully get into what is a tensor because we get into that in the general relativity course. But roughly speaking, the correct mathematical definition, which I assume is not particularly useful for you, is that this is an abstract object that is really a mapping between bilinear tensor, between the two lower energy tensor and R, and the real number. The same way as I can treat a vector as a linear mapping between the coordinates and a real number, R. Now, if you put all the and this have certain quantities, especially the way it transforms under Lorentz transformation. So if you take the electric and magnetic fields, you can put all of them in the form of a matrix, which will be a 2-0 tensor. That's why it is these two upper indexes. The same way as I write a vector with one upper index, I write a 2-0 tensor with two upper indexes. So it's F mu nu. The two upper ones is just 0, E1, E2, E3, minus E1, minus E2, minus E3. And then zeros on the diagonal. It's a symmetric tensor. And then it's a B3 minus B2, B1, and then a minus B3, B2, and minus B1. It's an anti-symmetric tensor, of course. Now, the thing, again, just to annoy people such as myself, the definition that is in common use in astrophysics textbooks is the same, but with a minus sign. So F mu nu astro is minus F mu nu particles. Since right now we're doing particle physics, then I'm going to use the particle physics convention. But if you saw that in E&M, I wouldn't be surprised if you saw that with the opposite sign. Why? Because now there are various advantages of that, especially that it shows much easier the way fields transform under Lorentz transformation and enable to derive the transformation law of fields for different observers. I think you might be doing that in advanced E&M course. Am I right? Or you never, who never saw this before I introduced this notation? Please raise your hand. One raises hand. Does that mean that everybody else have seen this Faraday tensor before? Yes, okay, very good. Faraday tensor. So now we can write the Maxwell's equation in a much more compact form. And for that, we first introduce another 4 vector, right? We already introduced several 4 vectors, right? Location, velocity, momentum. Now I'm going to introduce another one, which is called the 4 current 4 vector. And it's another with a J, mu, it's a 4 vector. That means that it transforms the same way as other 4 vectors under coordinate transformation. And the definition is, I'm putting out the C, though I don't have to because it's a neutral unit. It's rho, charge density, right? And J, current. Rho here is charge density. And J is the regular current. Now I can write down two of Maxwell's equations, the non-homogeneous Maxwell's equations, right? So the non-homogeneous Maxwell's equations, nabla dot E equal to rho, and nabla cross B minus TTE equal to J. I can write them in a very compact form. It's just d mu f mu nu equal J nu. Very simple. I assume that if you've seen Faraday tensor, then you've seen this notation. Is this assumption correct? Have you seen this before? Please raise your hand if you did see this before. 2, 3, roughly half. So half did not see. Okay, well, it's you just have to plug it in, right, and use the special relativistic formalism that we discussed, right? So, for example, if you take in this equation nu equal to 0, right, nu equal to 0, right, then we have what? D0, F00. What is F00? Remember, right, we have here nu equal to 0. That means that d mu f mu 0 equal J0. Now J0 is rho, right? So this is rho. Now here, remember, there is a summation over mu, right? So we have D0, F00. What is F00? What is F00? Guys, what is F00?
0.
0, right? F00 is 0. So we have here D0 F00 plus D1 F10 plus D2 F20 plus D3 F30 equal to rho. Now this is just 0. What is D1 F10? Give me another name for D1 F10. What is F10?
E1.
E1. And what is D1?
dt. Oh, dx.
Dx. Right? So this is just dx ex. What is the second term?
dy ey.
dy ey. The third term?
DZ easy.
dz easy. Very easy. So if you combine all these three together, what do you get?
Divergence.
Yeah. So just that blah blah dot E. Right? Divergence of E, which is just rho. Right? So I'm not lying, right? If you take nu equal to 0 in this equation, then you end up with the first of Maxwell's equation, non-homogeneous Maxwell's equation, Gauss's law, right? And if you take nu, which is different than 0, then I'm sure you're not going to be surprised if I tell you that you end up with the second of Maxwell's equation that's written here, right? It's the Ampere's law. So this is one compact form. This is only two Maxwell's equation. There are 4 Maxwell's equations, so we want the other 2. So the other 2, the easiest There is more than one way to introduce the other two in this notation, but the easiest is to introduce yet another 4-vector, which is the potential 4-vector. 4-vector potentials. Now you have seen potentials, right? Again, you should see that in one of your E&M courses. Did you see it? The vector potential and the scalar potential? Which course? Which course?
Electromagnetism, first year.
First year. Okay, it's very easy. So in magnetic field, we can always write as the curl of a vector potential, right? So we have B is equal nabla cross A, right? This from that, the Gauss law of magnetization automatically follows because there is a mathematical identity that the divergence of a curl is always 0, right? Because nabla dot nabla cross A is equal to 0 for any A, right? Any vector. So we can use this in Faraday's law, right? So Faraday's law. Right? Nabla cross E plus dTB is equal to 0, right? I can write that as nabla cross E plus, well, if I want to be 1 over C dTA equal to 0. Now again, the curl of a gradient is always 0. That's a mathematical identity. So again, nabla cross nabla of U, right? A scalar function is always 0. That's a mathematical identity. Right? Then we can write that in terms of the gradient of a scalar potential. That E plus dTA is the minus gradient of phi. All right, so phi, this is a scalar potential. And A is the vector potential. Now, as you said, you've seen that in first year. Now, the thing that I'm less convinced that you've seen in first year is that you can take all these, the scalar potential and the vector potential, and merge them together, and you end up with a 4-vector potential. So we can define a 4-vector potential. Right, A mu from the scalar and the vector potentials. Again, this is a 4-vector. It has all the properties of a 4-vector. And using this, we can now write down the remaining 2 Maxwell's equations, right? The Gauss law of magnetization and the Faraday's law. So the homogeneous Maxwell's equations. Nabla B equal to 0, and nabla cross E plus dTB equal to 0. I can simply write them as F mu nu equal d mu a nu minus d nu a nu. Did I mark it down? So we have a very compact form for Maxwell's equations. Now, in fact, I can also use this 4-vector potential to write down the inhomogeneous Maxwell's equations, which I wrote above, right? D mu F mu nu is J nu. I can just plug in F mu nu here. And we end up that the inhomogeneous Maxwell equations right? Just d mu F mu nu. So I can just write it down as d mu A nu minus d mu A mu is just J nu. I know it looks a little bit abstract, but there is a good reason why it is like that, and it's going to be simplified very shortly. So, but first thing first, so we have an operator which looks like d mu, one is lower and one is upper, right? So the operator d mu, right? This is really, what is written here? It's 1 over c squared dt squared minus nabla squared, right? So this is normally noted as a square. And it has a name. This is called the D'Alembertian. This is the generalization of the Laplacian from 3 dimensions to 4 dimensions. Right? That's the analog. Okay, so the 4-dimensional Minkowski space analog for the analog to the 3D Laplacian. So using this notation, we get that D'Alembertian of A nu minus d nu d mu A mu is equal to J nu. Now I still need to get rid of this second term. And how am I going to get rid of it? How am I going to get rid of it? Any suggestion?
Gauge it away.
Exactly. There is this thing called gauge transformation. Now, did you see gauge transformation? Who have seen gauge transformation? Please raise your hand. 3, 4. Okay. Half saw, half did not see. Okay, but before that, I'm not going to do the gauge transformation now because we don't have time, but I do want to have a few comments which are going to be very useful. So point that I want you to pay attention to. What we're doing so far is just classical E&M, right? Now we're going to do the quantum E&M on Tuesday. Now, the important thing is that, in classical E&M, I don't know if the thought ever occurred to you, right, when you learn that. The fields are the important entities. I mean, this is what we're measuring, essentially, right? The potentials are, I don't know, I remember for myself as a student, it looks a little bit like a nice mathematical construction, which is not, I did not really understand why doing it except for the mathematical fun, if you find it fun. Apparently, when it goes to the quantum world, it's the potential that becomes the important physical entities. And in fact, there are some effects which depend only on the potentials or directly on the potentials. And the most notable one is the Bohm-Aharonov effect, or the Aharonov-Bohm effect. Bohm is David Bohm, and Aharonov is in Tel Aviv. I think he's still alive. Right?
Yes, he is.
Yes.
Yes, yeah. So in classical E&M, right, the physical entities are the fields, right? And the potentials are mathematics, right? In quantum physics, aka QED, quantum electrodynamics, the potentials become crucial. You're going to see that next week. Another advantage of this formalism using the potentials is that the homogeneous Maxwell's equations are automatically taken care of, right? They follow immediately for any potentials, right? Phi and A that satisfy the requirement we have. So the homogeneous Maxwell's equations are automatically taken care of in the potential formalism. So really, the potentials are not just the nice mathematical entities, but they are actually become quite crucial when we're doing the QED. Okay, I still need to do the gauge transformation, but this will take another, I don't know, 10 minutes. So maybe it's better to skip it to next week, and then we can start quantizing things. Any questions? Okay, I'm going to post your new homework. Should be to next Friday. Since my last deadline is going to be coming in very shortly, then I expect to have now time to start grading your homework. I'm sorry for delaying that. If you don't have any further questions, then I guess I can do the stop sharing and stop recording.